Okay, we are live.
Yeah. Cool. So where's the link for everyone to join? Is it in the LinkedIn or?
Yes, it's in LinkedIn.
All right. Yeah, I can see people joining. That's good.
Yeah, that's good. Very good.
We probably give a few minutes.
Yep, I think that makes sense. Let's give it a couple of minutes.
Just to give, for everyone to join.
Sounds good. Teymur, I see some people joining.
Yep, that's good. A bit dynamics there.
Yeah. Right, it is bang on 3 o'clock. So thank you for those who've joined us so far. But can we just give it a couple more minutes so we can get more folks?
Just 2 minutes.
Yeah,
2 more
very
minutes
good.
for.
Right. Should we get going, Teymur, or should we give it
one? We probably 1 more minute and then we'll get going, I think.
Okay.
That's
Yep,
good.
fine. No problem.
I can see just 3:01. Yeah, 3:02. Just in 1 minute we can get it going.
Yep, sounds good.
I think we can start, probably.
Yep, sounds good, Teymur. All right,
yeah.
Let's get going. Right. Very good afternoon, and thank you all for joining us today for the third of the Spotlight webinar series. I hope you're all keeping safe given the current circumstances. Just to quickly introduce myself, I'm Thiruvenkatanathan. I'm one of the co-founders and directors of LYTT. I'm very excited today to present on the recent leap we in LYTT have made in developing and delivering our new real-time multi-phase inflow profiling app that has already added several thousand barrels of oil a day to BP operations. The system is currently live in one asset in BP and has now been used to implement BP's first ever water shutoff operation purely informed by fiber insights. I'm here today with Teymur Sadigov, a super talented senior petroleum engineer from BP, who we at LYTT have had the privilege of working with over the last few months to develop and deploy this capability into field operations at BP. Teymur, would you like to say a few words about yourself?
Sure, Prat. Thanks for humbling introduction. Good morning, good afternoon, and good evening to everyone. Just a few words about me. I am petroleum engineer by background, spent 11 years in BP, working with multiple regions in various areas of well and reservoir management. I've always had a keen eye on technology, including things like automation and analytics of big data. And I've been lucky to get involved with developing and testing some of those new technologies here in BP with LYTT. It is super exciting, especially seeing those tech ideas moving from concept and idea stage to successful field trials and the end products in very short period of time. And we'll discuss one of them today in this webinar. So thanks for joining and stay tuned.
Fantastic. Thanks, Teymur. And thanks again for offering to present some of the recent field results today. So much appreciated there.
Okay.
All right, let's hop on to the next slide. I'm just going to go off video so the slide doesn't get covered, but I'll jump back online for questions. All right, let's get started. We have a packed agenda for today's webinar, and we'll kick things off with Teymur presenting an operator's view on what the business challenge actually is. This is to bring to light some specifics on why we consider this product as being a significant leap in the world of in-well fluid surveillance within the oil industry. We then take a deeper dive into the technology itself to better highlight what differentiates LYTT'S analytics. Up next is the most exciting piece. We show some real field results from one of the recent deployments that we've done working very closely with Teymur and his team in BP, where we use LYTT'S real-time inflow profiling app to not just get an understanding of an oil well's production performance, but use the insights to make real operational decisions that have already added several thousand barrels of oil equivalent today. Over to you, Teymur.
Thanks, Brad. So yeah, to start with, let's talk about why we need production logs and why we need to understand the zonal distribution of inflow. So as we drill wells kilometers downhole, we get some static data to start with and estimate zonal production. As we carry on targeting new wells, drill more wells, that static data may become obsolete, and that result with wrong costly decisions around those target selections and spending millions, resulting with unintended negative surprises. So without getting up-to-date production logs, especially when we have got complex and constantly changing dynamic reservoirs and wells with multiple zones flowing into single wellbore with long production intervals. Today's practice on conventional logs, production logs, is usually one snapshot data for a few days of logging for every 2-3 years at best, even less sometimes, depending on is it onshore, offshore, or other influencing factors. And in the world of oil fields becoming more complex, like we go deep water, subsea, this is not enough to inform, this frequency is not enough to inform regular optimization decisions, and not enough, even sometimes maybe misleading as data becomes outdated and not representative. Production logs, when we do them, they do involve huge amounts of resources, time, people, equipment, and introduces logistical challenge and also HSE risks. It requires stopping production, intervening into wells, and that also involves risk of getting stuck in the hole, losing piece of tool string in the hole, and even sometimes hole access prevents to perform any logs at all. And even with successful intervention, inflow profile from conventional logs may not be fully representative depending on the completion type. I think in my experience, all these factors usually turn into inefficiencies, production deferrals, and surely larger operational expenses, larger than anticipated. And if you ask any subsurface engineer like me, what information would be useful for reservoir performance optimization, first answer is the production log. And if the question is when you need that production logs, the answer would be usually as soon as operationally possible. However, getting this information frequently is usually not more than a wishful thinking, especially current cost climate, as acquiring this data through intervention is quite expensive and challenging, as mentioned. And that's when we had lots of needs in the field for production log, and when we sat with LYTT team to understand if there was any way we can use like fiber we have as an alternative. We began by painting what we thought would be an ideal scenario, which is to have production logs not just once every few years, but just get this live every second, like downhole camera, giving us just ears in our wells. So this seems like a bit impossible, at the start as a task in our minds, but our light colleagues took us serious and turned this the visual thinking into vision and aspiration, and carried on working on this vision. And it didn't take too long before the light presented the first demo of the tool that we couldn't quite believe at the start what we saw, and it looked like real-time PLT. Yes, real time. That was a big wow moment for us when we saw first. And then where we are now, so basically no quarterly or monthly logging, but we just have 24/7 real-time inflow profiling in our wells. That's production log every second for you. So this is super useful, as mentioned, as we not only can now make long-term decisions around interventions and well target selection and drilling, but also just the day-to-day production optimization. And for interventions, yes, that means for future, no cost of running tools downhole, no HEC and execution risks, no interruption to production. This is real-time, non-intrusive, and of course, the reduced operational expenditure that associated with those interventions. And all you need is really the laptop and internet, and don't even need to go to office these days. So that's all you need to get the insights. Yep. Over to you, Prad.
Thanks, Teymur. When we first talked about this, we were quite nervous about committing to it, and we just said we'll try our best, pretty nervously, but try our best we did. Right. So before I jump in and discuss the algorithms behind our inflow profiling app, I think it would be useful to quickly refresh what LYTT'S offer is and how the inflow profiling app that we will talk more about sits within the data framework that's been built. What we offer in LYTT'S is an integrated cloud-native software for real-time feature extraction and pattern recognition on distributed fiber optic sensing data. Starting from left to right in the image here, we have fiber optic cables that are deployed in well as part of the well completion. These fibers are then connected to optical interrogators on the surface, usually for distributed acoustic and temperature sensing, DAS and DTS in the image, that convert the optical data into acoustic and thermal profiles along the length of the fiber. For those who are familiar with DAS or distributed acoustic sensing, you would know that one of the biggest challenges with DAS is big data. And when I say big data, I mean big data. Each DAS instrument typically generates acoustic data of close to 1 terabyte an hour. This is nearly 1,000 movies worth of data every single hour from each and every sensor. LYTT'S offer starts from what we refer to here in the image as the RTPU, the real-time processing unit, which is an edge computer running LYTT'S proprietary real-time feature extraction software that intelligently distills just the most relevant features in the acoustic signal in real time. This reduces data volume at site by over 1,000 times without, and I repeat, without, losing the most relevant strands of information required for patterning multiple in-well fluid events of interest downhole. This feature-rich dataset is then streamed into our cloud-based streaming analytics software that converts these acoustic features into user-friendly logs using LYTT'S proprietary machine learning-based pattern recognition models. Think of this as the layer where we convert the acoustic features into something more meaningful for the end user, like a downhole sand log or a flow profile, using specific algorithms that we refer to in the LYTT world as apps. These logs are then presented to operators in near real time, sometimes alongside other sensors like choke, downhole pressure, in a time synchronized fashion to help operators make effective decisions in real time. A key take home here is that we don't just present acoustic data, we present insights, and we present it in the form of logs or real-time logs, like flow profiles or sand logs, that can then be used to inform operational decisions, like optimizing the pressure in your well in real time to improve well performance. All right. The question I often get is, how on earth do you know what the signature or pattern of the acoustic signal is for gas and water and oil? So here it is. I'm now going to let you in on our secret sauce, the black magic. We use what we refer to in LYTT'S hybrid modeling or hybrid analytics, where we use a combination of machine learning and first principles physics to pattern and define signatures of different fluid types. Let me explain what I mean here by starting off with a computer vision type challenge that many of the data scientists in the audience may have come across before. What you have on the left here is an image where we try to use machine learning to identify and differentiate between a bus, a car, and a pedestrian, as you can see. This is usually addressed using supervised learning models, where a whole bunch of labeled data containing multiple images of each of these classes are used to train a multi-class classification problem. And then the model is used to predict based on how close the patterns that it sees in the real world are to the training data. In our case, however, we don't quite know what a gas or water entry in an oil well actually sounds like under different well conditions in order for us to use that knowledge for training. So to get some label data, we at Light have run hundreds of experiments simulating real-world reservoir conditions in a flow loop type setting to better understand what each of the fluids actually sound like under different scenarios. And that's the image that you see uh, to the right of the image on the left. It's the one in the center. So to get some labeled data, we have run many experiments, and these are to simulate different well scenarios. And what we observed was quite interesting. We noticed that the same fluid can make very different acoustic noise depending on a number of factors, completion types being one of them, fiber location, and also the background flow itself. So we began patterning these signal variabilities to capture the envelope of the signature envelope, as we called it, for each fluid type. And we didn't just stop there. We took it one step forward to then reason why we see the signatures we are actually seeing using first principle physics. This let us better calibrate the lab data to the field data. And the thinking here has evolved quite a bit for some of the applications like downhole sand detection, but it's still evolving for a few like inflow profiling. We are now able to explain why sand entry sounds the way it does and how that translates onto a signature on DAS with clarity around how this would then change in different environments. Pretty impressive, pretty sweet, isn't it? All right, so I've got a video here which I'd like to show, but before I go into that, this is showing the inflow algorithm in action. We realize that arriving at one model that describes and provides an inflow profile could be quite challenging. So we started off by chunking the problem into smaller pieces. We did that by addressing three fundamental questions. One, where is the inflow coming from? Two, what is the fluid type? And three, how much of each of the fluid types are we seeing in flux? So we built three model cases, one for each of the questions. So one for the where, one for the what, and one for how much. And here's a real field example of the inflow detection model in action that addresses the first of the three questions. Let me jump onto the video. Just give me 1 second. Right. So what you see here is noise made by the inflowing fluids generated using data-driven methods applied to both temperature and acoustic data acquired in a well that has three production zones. We see choke at the bottom in red and the dynamic inflow of fluids presented as a heat map with depth along the vertical axis and time along the horizontal axis. You can see how the well's production intervals and flow dynamics change as we ramp up the well, giving clarity around when each of the zones come into production. This video gives an indication of the first of the questions that we talked about, the where, but we've now delivered models to answer the other two as well. So questions 2 and 3 to provide a dynamic real-time multiphase inflow profile for the well. These insights have also been used to implement the first water shutoff operation in BP, fully informed by fiber optic data that has been executed by Teymur and his team that I'll let Teymur talk to in the next slide. Over to you, Teymur. Just give me 1 second. Let me move to the next slide. Yeah.
Yep.
There you go. Right. Over to you.
Thanks, Brad. Thanks. That was a really interesting one. And what I will cover in this slide is how we work together with Light in agile way to get where we are today, from emerging business needs to start with, such as sudden and unexpected well performance changes and resulting challenges that we managed to timely address by fast track delivery of the working product in increments. How this helped providing insight into well optimization and intervention. Yeah, it's quite a busy slide, and this timeline I'll walk you through one by one. And at first, it was great to see the initial version of the model ready that answered the first of three questions that Prad mentioned earlier, where the flow is coming from. This was already ready to be deployed right on time with a well startup. That's what you see at the bottom left corner that Prad showed as an animation. Just to remind again, what you see here is the color histogram. Y is depth axis, and on the X is time axis. And then we carried on with producing well, and with well performance challenging did grow more complex, especially with early water production. We needed to act quick to maintain well plant stability and to keep production at max in the meantime. Understanding water source, where the water is coming from, was crucial. So we know now, where the flow is coming from, but now we need to understand which kind of phase is coming from where. We kept the engagement live with regular check-ins with Light, discussing through the emerging issues, questions on the well performance, keeping constant feedback loop between the asset team and the Light was key here. And I think it was a big part of our success for fast-tracking the model development as well. And in the meantime, we got also the phase identification model that was already being built in the quick turnaround, which helped us to asset team to consolidate our thoughts around reservoir inflow and the water producing zone in addition. And this model version of the model answered the second question. So what is coming from, specifically which phase of fluid in addition to where is the flow coming from? And that's what you see in the second picture at the bottom left. That's also color histogram. Here you see that the brighter events are the flow, the change in the flow and the phase. And with those initial insights from the combined inflow allocation and the phase identification models, we successfully informed the well drawdown optimization to add several thousand barrels of oil a day extra production with reduction on the water for temporary periods. So, and that's what you see at the third item in the timeline, red-blue color histogram in the upper left corner. And you can observe here the changing inflow through time at the certain depths. And that helped us to allowing the optimizing drawdown and finding the sweet spot for the maximum oil and less water. So while drawdown optimization benefit was intermittent due to the water influx mechanism, we carried on thinking through a water shutoff option. As water kept climbing up, it continued to increase up to 80%. Insights around the water influx zone was crucial to inform the next action, which is water shutoff intervention. And by the time we've already got the fully developed, while thinking through these issues and challenges emerging, we've got the fully developed now inflow allocation, phase detection, and also phase quantification models, to answering all three questions that we mentioned earlier. Basically where, what, and how much, which that turned what you can see on the plot here, the fourth item in the timeline in the bottom right corner. In addition to the color histogram, you can also see the water allocation per depth and oil, and also in the quantification on the x-axis. So using all this input data, decision was informed, and we went ahead with water shutoff intervention. And as we have fiber across whole depths from surface to bottom of the well, we were able to actually monitor the intervention progress, which is what you're seeing at the next item in the timeline, upper right corner. So you can see there basically the tool string running in hole, and then the hold stations at certain depths as the team was executing the water shutoff scope, and then pull out of hole. So you can basically monitor intervention in the real time, see what's happening. And the last point to cover in timeline is the initial results of the production data. So during restart, once we finish the water shutoff intervention, during restart after water shutoff intervention, looks quite promising. And with no water, after isolating the water influx zone based on fiber-driven the production log, so no water added twice as much as drawdown So that kind of validated the water inflow prediction and the zonal inflow allocation. So currently, we're monitoring the well performance as we've been off the well further. Looking back on this timeline, in retrospect, what was quite fulfilling is really the fast-paced delivery of those incremental progress of this fiber-based production logging model. Each increment delivered arriving on time to meet emerging business needs, as we had the one issue after another hitting us, and answering all those questions was changing well dynamics and informing all the decisions we've made along the way. And I think this is the great example of delivering business value with the kind of agile way of working. Over to you, Prad.
Thanks, Teymur. One important takeaway here is how the streaming analytics and the pattern recognition framework that we have in place was used along with the flow loop data to turn results around quickly through an agile delivery model. Again, a truly refreshing and a transformational way of working that has led to some game-changing capability and results. So thanks very much, Teymur, for your help with that. All right, so moving on to the next slide. This brings us close to the end of the talk today, but before we open it up for questions, I just wanted to say that this is the first of the three-part webinar series on inflow profiling. The second will be offered by two of our bright young emerging talents, Char and James, who will present a deeper dive into the current capability stack, highlighting some of the extensions of the flow profiling capability for different well scenarios, along with some of the limitations that we're currently working to overcome. We see this as a journey towards getting to the dream of the real-time production profiling in all completion types and fiber configurations, but we're just not there yet, but we are working very hard to get there. We have started the journey, so let's hope we can get there soon. The third talk will be from Alessandro, one of our bright data scientists, who will be joined with Vishnu, our maverick data engineer, who will talk about how we convert the models into apps for real-time streaming analytics. We also now have a joint paper with Teymur and his team at BP that gives far more detail on the field results shown here that has already been accepted for presentation at the SPE ATC 2020. So for those who want to catch more of the results, please do visit us and welcome questions then. For more information on our products, please visit lytt.com or feel free to write to me at prad@lytt.com. With that, we open it up for questions. And maybe I can switch on my video as well so you can see me. All right. Okay, there are a few that's already come in here. So let's start with the first one. How have you validated the outputs here? Maybe it's a question that you can take, Teymur.
Yeah, sure. That's a good question. That's actually the immediate question we asked ourselves to see as per the well flow rates after the intervention whether our predictions were valid. What we saw during restart was that we doubled the well drawdown without any signs of water and actually any signs of inflow, in addition to no water from the zone we isolated. That was really a kind of proof point for our predictions were valid in terms of the water detection and identification. Also, when we compared the well flow data, the results post water shut-off restart with the multilayer inflow model we did earlier, that we used the fiber production log as an input, it was spot on, kind of full match. That also was a proof point about inflow allocation in addition to water detection and phase identification and the quantification. So that two, the key, the facts were a kind of proof point for validation. That was quite promising for future as well.
Very good.
And again, it's a bit, can't share too much details here because of confidentiality, but as Pratt said, we have the paper coming in the SPE ATC 2020, which will have much more details in it.
Great, Teymur. So I have one from Don Craig from BP. What happens to the DAS data that is not stripped out from the RTPU process? Does the unused data get stored for future access or is it discarded? So the way we work so far, if we know what events are of interest and if we believe the feature sets that we've got are enough to capture those, we would end up discarding the raw data, Don. But in cases where it is required to store the raw data, that is something we can offer as well. But again, that you will end up having the big data challenge. And so transferring that, we are having some thoughts on how we can transfer the raw data as well. But at this point, we are discarding them because we are confident enough to use the feature sets that we extract in real time for sand and flow profile applications. All right, there is another one. Do you see considerable variability in the flow dynamics, and how important is a dynamic measurement to well optimization? So maybe this is one for you, Teymur.
Oh, good question there as well. Yeah, one thing we realized with multi-zone inflow profile prediction is quite complex in multiple dimensions. It is heterogeneous across flow interval. It changes through time. It even changes with various drawdown at any point in time. So hence, like we said earlier, the conventional production logs are usually taking snapshots at 2 nominated drawdowns, and which would allow to miss easily the insights from the wider range of the flow conditions. And with dynamic measurements like fiber production logs, fiber-driven production logs, you get the full range. And with full range available, you can easily assess and pick the sweet spot for maximum production. And picking the sweet spot is not always intuitive. Like rule of thumb, for example, more drawdown means more oil, and it's not always the case. Which is where the dynamic measurements like fiber production logs are quite helpful.
Okay, very good. I'm just reviewing the questions.
Hope that answered questions.
There's one here which is from Sina, which is it DAS based only, or do you take temperature as input too in your model, as some inflows may not generate sound and shows in temperature only? So for the inflow detection model that you saw us showcase before, Sina, this is a hybrid model. So it's taking both DAS and DTS as inputs. And what we want to do is get to a point where we take both when we have the opportunity to do that. But there are instances where you just have one fiber across your reservoir, and so you may have to switch between DAS and DTS, and we have ways in which we could potentially look at getting DAS and DTS. But having said that, we drive the results using one and then complement using the other. Hope that answers your question. Another one. Let's just go through the questions here. How closely, this is from Dennis Drea, how closely must your flow loop simulate a specific completion type to provide effective fingerprint information? So this is, again, this is what we briefly discussed about before, Dennis. So what we try and do there is not just look at the pattern as we see it under different flow conditions, but what we also do is try to understand why we see the patterns we see to then better calibrate that for different well scenarios. So we've gone a long way with that in sand monitoring, but for inflow profiling, it is a very complex challenge to model it out from first principles. So we're trying to evolve the thinking there, but at this point, what we've got is a fairly good understanding of how to normalize the data and calibrate it for field conditions, which is sort of what we've been using, and we calibrate that. For sand, as an example, we have an auto calibration sequence that sort of understands what the baseline of the well looks like, and then calibrates itself automatically. And we're trying to get there with flow profiling applications as well.
There's also a good paper out there from LYTT'S about the sand applications, which is the SPE paper 188991. So you can refer to for some good field application on the sand detection from LYTT'S.
Yes, and that was again something we'd worked with Teymur when he was in Azerbaijan. So it's a good paper to have a look at, I think. Yeah. Okay, let's look at the next one. You mentioned flow loop tests. Just reviewing these questions that I'm seeing. How many assets are you live on? That's a good one. So this is the first time we're doing this, and this is the first asset we delivered the solution to, and this is already added, as Teymur mentioned, several thousand barrels of oil equivalent today in the well that we tried it on. We are now deploying it in the second, or the plan is to deploy it in the second asset, and we are getting ready for it as we speak. And we are looking to scale it, but again, we want to take it in steps and make sure that what we deliver adds value to our clients.
And I think this is first asset for inflow profile, the
Yeah.
fiber driven. I think there are many other applications across the world, as far as I know. You guys have, right?
Yes.
Yeah.
That's right. Okay. And then,
Some good questions there.
yeah, some good questions. And there's another one coming up, which is how do you handle the system noise in your methods, as it can vary case by case? And this again is from Sina. And I think the answer is broadly in line with what was said before. So in terms of calibration, what we try and do is um, we have our calibration sequences, we have our normalization sequences, which sort of get applied on the data to try and normalize for the effects where you see, if you have more optical input, your baselines would change and all of that gets normalized. So we have methods in which we could do that, and those get applied in real time as well. Okay. And there's one, how do you distinguish water and or low oil rate by DAS? Low oil rate is relatively quiet. Good question. So this is something we are looking into. Honestly speaking, in the case here, it is a high rate environment, and but having said that, we are detecting lower volumes of water too. It's just the rate quantification and what the limits or the thresholds are something that we are investigating. And I would say this is more relative. So we could have a percentage type number that we can project, but we'd like to verify that before we go in and do that. Okay. And then there is one conventional PLT has its own inaccuracies usually. Do you believe your approach will be more accurate than measurement with PLT? I'll probably defer that to Teymur.
Yeah, I think it's from experience. It depends on the scenario. I think it depends on the completion type. It depends on the flow conditions and operating envelope, GOR and gas. I think those are the key crucial influencing factors and into whether your conventional PLT would be applicable. Like in the completion types with a limited entry, multi-zone limited entry, where actually conventional logs would be not representative, where the fiber-based PLT, which is strapped on across the full length of the completion, would be more representative. I think I would answer it depends. And most of the scenarios, if you compare, my view would be that the fiber-based PLT would be more accurate. I think it will build also accuracy through time as we get more and more cases of validation. And as you said, like your model gets trained by and improved by more data coming in.
Great.
Would
Thanks,
that be fair? Anything to add, Prad, on this?
No, I think you summarized it. The biggest disadvantage here is the fact that you're seeing dynamic measurements, and with the production logging tool, you get a snapshot. And just looking at the profiles that you just saw, you would see how the dynamics change in the well through time. And in some scenarios, you won't have as much of a change, but in many scenarios you will. And so it is important that we understand what we've seen in the data.
And that more data, more range, that means the model self-trains itself quickly to become much more mature. Yep.
Great. I know we're running short of time here, so I'll take the last question here, which is around flow regimes. This is from John Gaskell. Do you have any general responses that show changes in the flow regimes as well? The answer is yes. So we can pick up things like slug. We can begin looking at regime changes, but again, the length and breadth of that is not something we've analyzed threadbare just yet. Having said that, we've been focusing on the inflow profiling capability, but that is definitely something we can look at from a flow assurance perspective. We haven't done that just yet. Okay, with that, I think we've already 7 minutes over. So thank you so much for joining us, and hope you all enjoyed the session. And please do dial in for the next one as well. And we look forward to having a lot of you then.
Thanks all.
Thank you all.
Thank you. Thank you.
Bye.